Okay, thanks much for coming. We do have an overview of research projects, and there will be presentation by Dr. Khan about molecular dynamics of reactions and another new project that will get a prize for everyone. So please consider to make some comments. Future improvements.
Okay, so basically I have two parts. The first part, I'm going to deliver some bad results. So I will need your advice on how to improve to get the right computational results. So for the second part, I guess we have relatively good results. I guess I need your opinion just to let me know how to finish this project. So maybe we can write a paper about it. So this is the first one. So for the first one, we focus on ab initio molecular dynamics to get some ideas about methane combustion. And we just use ground state molecular dynamics. So, and our calculation is at high temperatures, ranges from 2000 Kelvin to maybe 4000 Kelvins. So this is my first model. This is methane and oxygen. This is the cell size. So the right part is a snapshot at 1000 foot per second of the ab initio molecular dynamics trajectory. We can see there are some products like here, and also we have some water formation, and also this HO2 species. So
what's do you welcome questions during the
yes?
So your note on 2500 Kelvin, is it before reaction or after reaction?
I didn't check, but this is
Initial condition.
condition.
Do you expect to an increase of the temperature at the end?
Yes, but I guess the increase will not be huge. There might be some fluctuations like 300 or 500.
Do you expect watching movies of the reaction dynamics is fun, but not super productive? Do you think just watching the temperature as function of time would be sufficient to identify when exothermic steps are occurring?
Yeah. Mm-hmm.
So, how many waters?
Not much. I guess maybe during the trajectories, maybe two or just one water information. We cannot find it here.
But it's clear that maybe it's over the boundary,
Right.
but
Maybe this one, but it's not a perfect angle, so you cannot see the other hydrogen.
okay. And for these conditions are not sufficient for carbon dioxide or monoxide to form.
In fact, in all of my calculations, I do not observe the formation of carbon dioxide or carbon monoxide.
So
Because maybe just because just the limitation of the trajectories, I should just increase the duration.
What is the density in respect to like density of water? Liquid water. Is it like more or less than gram per cubic centimeter?
Get into the calculations.
So at this temperatures, it should be a gas or supercritical liquid, but they are so densely packed that it is at the limit very close to a liquid. And the ratio of 1 methane to 4 oxygen is the stoichiometric to convert everything into carbon dioxide and water, or
for this one, my consideration is because methane has 4 hydrogens, right? So each hydrogen should be paired with 1 oxygen molecules. That's just my thought. I
Okay,
guess
so-
maybe
but-
experimentally they can just vary the concentration of oxygen so that the final product will be different.
okay.
Because experimentally they have oxygen-rich condition.
Just a second. It it's probably David will do it quicker. Should
So
it be
what I'm looking at, you do have excess oxygen, but not very much excess.
Mm-hmm.
You're pretty close to stoichiometric. But I'd have to look up this reaction specifically to make sure of that.
Should it be 1 to 2?
Yeah, that's the math I'm coming out to as well. Is he's got about double the oxygen what he needs for stoichiometric.
Mm-hmm.
So like each
But I
carbon gets 2 oxygens, and each 2 hydrogens get one oxygen. And if balancing, it should be like,
Yes.
okay.
I'm thinking maybe that's the reason why there is just a limited number of reactions, because every hydrogen is in the triplet state, right? If you have more oxygens, then it's probably difficult to bring all of the oxygen to the singlet state, right?
Maybe. And since reactions are not easily getting through molecular dynamics, maybe it's better to get into right away from stoichiometric.
Yeah.
How many HO2s are you seeing about?
I guess during the trajectory, maybe just 1 or 2 water molecules.
You mean HO2?
No, HO, the HO2, the,
Hydroperoxide?
yeah, that thing.
And I guess for this one, next time I'll just decrease the concentration of oxygen to see what's going on. I guess for this one, because for this project, our main focus is on catalytic combustion reactions. So finally, we want to put the oxygen and methane over metal clusters. We want to see how the metal clusters can change the activation barrier of this kind of reactions. So here, I use this reference to show you the combustion reaction is really complicated. It involves different reaction channels. So like here, there is just one massive molecule, and we have like 5 different channels to stay on the surface.
But there are literature support for activating CH bond and going into methyl group rather than methane. Okay. And one doesn't need metal catalyst. It happens on the semiconductor surface.
My feeling, as long as there is oxygen on the surface, then the reaction should go through.
So one can make catalytic burning, catalytic combustion on the surface of this metal oxide.
Yes, because if you have oxide, then this oxide can just attract the hydrogen of methane. Otherwise, this kind of reaction, this kind of bonding cannot happen.
And this breaking of CH bond happens on different surface sites, just as its energy is different.
Yes.
So it will be anyway more energetically favorable than in the vacuum.
How to pronounce this word?
Huh?
How to pronounce this word?
Which one are we looking at?
Heterolytic.
Heterolytic? Yeah.
I guess this is unsuccessful simulation. So here is my simulation cell. It's a little bit bigger, larger than the previous one, and we have 10 methane molecules for the oxygen molecules. So I guess the temperature is also a little bit higher. So here I use 3000 Kelvin. But during the definition molecular calculation trajectory, basically I see no reaction at all.
I have a comment. It's not a question. It's very vague. I don't have time to crystallize the thought. Remember the paper that Wendy Sub did about metal organic frameworks and molecules living from the container? So she was doing it based on the classical physics completely, considering molecules as hard spheres living this container. So if one does this a little oversimplified thing, then one can get how frequent molecules collide. And if we do have the activation barrier height to overcome and kinetic energy of molecule, then maybe this amount of kinetic energy will be sufficient to overcome the barrier and launch the reaction, but the density is so sparse that during the simulation time there was not enough time for right molecules to collide. So it should be very much dependent on the density, and for naked eye it looks distance between atoms about twice as larger than in the previous books. So when you may compress it like 2 times, maybe not in one step, because in one step it will just explode, but compress, run dynamics, compress, run dynamics a little.
Yeah, because it looks like one of your molecules is trying to make CO2 on the far right.
This one?
Farther right, on the face. Yeah.
Oh,
So if we can find a way to get rid of those hydrogens.
if this is maybe if one will go a little further, it will go further because this methyl peroxyl is the tallest. How to say? It's right after the transition state. This intermediate is takes highest barrier to form, and if it is formed, it should avalanche and do chain reaction for the rest. I didn't share it, but I saw online there are like half dozen papers on femtosecond spectroscopy of this intermediate. So it's detected experimentally, and one can follow what it does on the short time of reaction.
Still, I'm a little bit surprised about the difference between experimental and computational, because experimental they use gas phase, right? So that means the density is much larger. Our much smaller than our calculations, right?
But if you try to ignite something physically in the real world with a lighter or much, it takes like several seconds. So it's very slow. And here we are looking on something like hundreds of femtoseconds.
Yes, but the temperature is also much.
It's frequency of collisions. So if this density prompts that it's one collision per like 1 picosecond, then half picosecond will never get to reaction. And it is one of our approximations that we intentionally increase not only temperature but density to make them to collide more frequently and explore these teammates.
Okay. So here I just want to include the metal clusters into our simulation cell, and I prepared two initial configurations. This is a almost perfect octahedral metal cluster. I put it in the center of the cell, and here it's in the left corner of the cell. Even though we have periodic boundary conditions, these two configurations are quite different. Because for this one, methane and oxygen are kind of evenly distributed in the simulation cell. And here, the methane molecules are kind of confined in a certain area, and oxygen is distributed evenly.
So which of the reactants seem to have more preferred binding to the metal? Oxygen or methane?
Oxygen.
So you see that oxygen is bound to metal and methane is floating around.
Yes.
And if in the literature paper that you were showing in the beginning, methane does adsorb to the semiconductor surface.
Yes, but for that one, you still have the barrier to overcome, right?
So if one makes an interface between metal and metal oxide, there is a chance that oxygen will adsorb to metal, methane will adsorb to oxide, and on their interface there will be like border nodal line of combustion.
Right. interpretation is at least there will be some molecular interaction between oxygen adsorbed on the surface
Uh-huh.
with hydrogen of the methane molecules.
Does the system warm experience any increase of temperature when oxygen adsorbed to the metal? Like if you would use aluminum cluster instead of platinum, probably it will burn. The amount of heat just for oxygen absorbing and forming aluminum oxide will just heat up the whole system. If platinum is noble, maybe it's not enough to launch the reaction, but maybe there is, if it is preferred binding, this amount of energy will be released into kinetic. You didn't notice them starting moving quicker.
I didn't monitor the temperature.
Okay.
I guess the oxidation of metal is a natural process, right?
On a long time scale corrosion, but here we speed up everything at higher pressures. It can go quicker.
So this is job optimization. And we can see there is some structural changes on the metal cluster. And here I show the application molecular dynamics calculations. I believe the temperature is 3000 Kelvin. So, 2000 Kelvin. So surprisingly, for this one, I also cannot observe any reaction events.
But there are some interesting observations. In previous slides, all oxygen molecules were in molecular intact form, coordinated to metal only by one of two atoms.
I guess we should compare
Yeah,
left around
the
with
first
one.
one
with this one.
And here, about half of oxygens are adsorbed. I don't know the right word. David can help us. Bidentate? It would be the appropriate word here or not quite. When both oxygens are bound to metal atoms.
If I remember, that's the right word.
And if they both are coordinated to metal, maybe their bond to each other is bigger and they're more ready to participate in chemistry. There is even an exotic shape when right in the center, when one oxygen atom is connected to two platinum, and then right in the zero Kelvin, the first panel right in the center of the metal cluster, top higher. Yes, this one. So it's total 3 links to metal. It looks like a step towards forming an oxide. So there are some structural changes, and in case nothing will work from this minute in calculations, the paper will be on oxygen coordination on surface of metal cluster.
Would you expect its spin state to change when it binds to the metal surface?
I didn't monitor the spin multiplicity. But I guess initially all oxygen is in the triplet state, since at this point they bound to the metal, I guess maybe we just transform to the singlet state.
And singlet will be not the minimal energy. In some sense, it is already excited.
Right.
On the second panel, it also looks like an O3 ozone molecule in the lower right. I don't know if it is sounds correct scientifically, but maybe it's a new way to generate ozone.
O3.
Yeah. Okay.
I'm quite surprised why the mass molecule is so robust under these kind of conditions. Because right now, the metal cluster is quite reactive, right? And the oxygen on the metal cluster is also reactive. But still, the methane is so robust.
Oxygen should catch one of the protons from methane when it performs high amplitude oscillations. So when the amplitude is high and when it elongates at the maximal distance permitted by given temperature, there should be an oxygen flying nearby to capture it, and so in some sense it is a proton transfer from methane to oxygen from this hydroperoxide. And it's, I don't know if you did assessment of the heights of this barrier, but it can be very, very tall. Also like half electron volt easily. And there are no quantum corrections which would play a role in the nature for Gish to have much lower temperatures.
But I guess for massive combustion, people just do not report. I guess for massive combustion, in the community, no one reports the importance of tunneling effects.
Oh, it's good. There is a chance to be the first.
Because here is another simulation. I guess I should. I remember there is a weak connection between methane and the metal cluster. Probably this one. It's just not the right angle. But I guess the distance between carbon and metal is like 2.2 angstrom. So maybe at this point there's some very weak interactions. Maybe for this one, maybe I can increase the duration of trajectories to see what's going on.
So it looks like end of the first part and other conclusions.
I probably will try different configurations. The first step is try different initial configurations like changes the concentration of oxygen, or just compress the simulation cell to make it more dense. And another, maybe I can try just increase the temperature a little bit higher. Yeah.
According to ideal gas law, compressing will automatically increase the temperature.
Yes.
So maybe one doesn't need to add to do the procedure of heating. So it's like PV equals constant T.
PV equals N constant T, but yeah.
Yeah. So if one
And it's treated as a constant in this situation, but
reduces volume,
if you reduce volume, temperature should increase.
Increase pressure, temperature will increase, and it may increase even more than we want.
Mm-hmm. But if we have the metal cluster, the compressing is not safe, right? It will make the metal cluster very reactive. It may explode.
Well, first we need to catch the target reaction to happen, and then we can systematically explore the conditions. And at these temperatures, it will be like liquid metal droplet. It sounds even better title of the paper. Liquid metal ignites.
Instead of using the metal cluster, I was wondering if we can start with just metal dioxide surface. Cause
Yes, and then one can make this trick of compression only in Z direction, so that the crystal doesn't break,
right,
which is not a problem. And we cannot do semiconductor metal oxide cluster because it will be very big. Otherwise, it will be reactive much more than necessary. Technically, we can take the titanium dioxide cluster from your next slide, from what London is doing. Try to use it as an efficiency. Okay.
guess here is the second part. So I guess for London, I only include this one, right? No,
Mm-hmm.
there is no organic part in this one, right?
He tried organic part about 2.5 years ago. Aaron was doing this organic molecule on the surface of perovskite and on a nanowire surface. And then London tried to do this combination, but didn't went too far and started complaining that electric field doesn't give convergence.
Okay. Okay, anyway, I guess for this one, for this project, we want to test how the charge carrier behavior will be different under different electrical field.
Mm-hmm.
So here is my model. This is perovskite, this is titanium, and this is the distance. So this is organic dye.
Mm-hmm.
And this is charge density kind of figure.
Is it total charge density or it
No.
is?
I use the total minus each component. So basically, I just want to show the binding
Mm-hmm.
between each component with the perovskite. So to indicate there is actual binding.
Mhm. And on the top, your titanium polyoxide cluster is connected by two links. Is it the same as London was doing, or you modified the model and found it?
I modified. I believe London tests two models, right? One is, I guess the titanium oxide is far away from the surface,
Mm-hmm.
and they call it through space.
Mm-hmm.
And the other one is through bond, I guess.
Mhm.
So I guess this model is a little bit different. Actually, there are three binding sites. We have oxygen with lead,
Mm-hmm.
and also there is a hydrogen bonding. Hydrogen is oxygen with iodine with bromine.
Mm-hmm.
So it's- so, as we can see here.
Mm-hmm. So it's hybridizes with the semiconductor as well.
Yes.
Okay.
And here is the petals. So the HOMO is contributed by the organic dye. The LUMO is contributed by the titanium cluster. So the cap is like 0.6 electron volts. This is without any external electric field.
So it's who is organic dye and who on titanium. So if a photovoltaic cell will be done, the maximum voltage from this cell will be 0.6 volt, no more, right?
So here is my calculations under external electric field. So I guess the electric field is applied on the z-axis of the model. This is minus 0.3 up to 0.05. So basically we can say the band gap is shrinking as we increase the electric field.
And the dashed line is Fermi energy.
Right.
So when you, for negative field, HOMO goes lower, and for positive field, HOMO goes higher and intersects the Fermi energy.
Mm-hmm.
So for positive values of electric field, gap comes to zero, and further HOMO and LUMO swaps their order. Is this information of density of electronic structure given a different voltage sufficient to generate IV curve, or something else is needed?
You get the open circuit voltage.
Yes, it can get the open circuit voltage, but can it reproduce the whole IV curve? Probably not, because there is no current. And
You could speculate, you know, like the maximum amount of power you could get from the difference in the band gap, right?
maximum voltage. For energy, it is area.
Right. That's what I was thinking, you somehow figure out the area you could solve for current, but probably can't get power.
To get the current one probably needs to get dynamics. Maybe we attach leads or hypothetically turn to equation. So where this consideration can bring us, what is expected or target results? Why it is better than no voltage?
I guess at this point, I just want to evaluate the influences.
Mm-hmm. So the numerical experiment that we can do with available tools without changing of the procedure is rate of electron, like photoexcite on perovskite, and then evaluate rate of electron transfer to titanium and hole to organic dye. Other expectations that change of the voltage will speed up or slow down this transfer of carriers to donor and acceptor.
I would think so.
And other qualitative, like in which situation it will get quicker and which situation it gets slower. Because on one hand, the resonance condition when from one orbital to another is less offset, it goes quicker. In this sense, the value when is and then since negative field makes HOMO closer to the rest of valence band, and it will be quicker.
Yeah, that's my opinion. For this one, you should have the quickest charge carrier relaxation. Because the density state is much higher, right? There should be more relaxation channels for this one.
Okay, so it will be a hypothetical expected result
Yeah.
if one runs molecular dynamic.
Mm-hmm.
And do you see any problems to run molecular dynamics in presence of electric field?
No?
So it should work.
Yes.
It was an unknown problem when I was complaining about it.
I didn't see any problems.
Okay.
What is he complaining?
She was complaining that with explicit electric field, it doesn't converge, molecular dynamics doesn't work at all.
I already have some steps on molecular dynamics, I guess. Maybe one from 200, maybe 1 or 200 femtoseconds, I guess. There's no problem at all. I guess next step I'll just run non-adiabatic couplings on these models, so we can have a comparison, a systematic comparison.
Mm-hmm. side question. If you plot the gap as function of electric field,
Mhm.
will it be linear or it will deviate from linear behavior? And
Do a simple experiments here.
now we are doing experiments right at the group meeting. You think we will be ready to tell something next time?
I hope so.
Okay. If then, if you want to stop maybe in a week, in 2 weeks.
Okay, in 2 weeks.
And since Kevin has a schedule conflict for Tuesday, probably we will schedule him for Friday. Also in a couple of weeks.
Almost linear.
Oh, it looks like, well, it looks like a line with a step.
Mhm.
Okay.
Almost linear.
So it gives maybe it is a good sign if the gap is linear in electric field, then the proportionality coefficient will be dipole moment, or some collective dipole moment, and it will be a signature that energies of orbitals can be computed without WASP, just as dipole approximation.
But how about the subgaps?
The dipole moments of different orbitals are different. Therefore, response of energy of individual orbitals on change of electric field are not equivalent. So, with large value of electric fields, the order of orbitals is changing.
Mm-hmm.
Like if one would put images of orbitals near each line, these like whatever was first will be like number 10th order of movement plus one can swap them further up.
Okay. Mm-hmm.
Okay. Yeah, it's very interesting, and it's very enthusiastic direction that needs to be completed and published before interest of community to perovskite disappears. Okay, let's please join me in thanking you.
I have a question. So
Yes.
for this project, is it necessary to do the non-collinear calculations? We just focus on comparison.
It's always good to have them. The qualitative results will not change, and acceptance of future publications will not be damaged. At one point, one can accompany regular calculations with non-collinear calculations only in a couple of points to show that qualitative trends are not changed. But if it is, if they cost the same amount of numerical effort, then it's better to do non-collinear all the time. If it is a drastic difference, then it's okay to save.
Mm-hmm.
With non-collinear, probably, well, Aaron is the best expert. Like Lumor was good by 0.1 or 0.3 or something like that. But no,
Maybe a little watt.
Luma will not split because Luma here is from titanium. The Luma associated with perovskite will split.
Right, so you might get changing of levels from there. So wherever your orange line, where this starts. So I guess that goes up to the band edge, because they kind of bond, right?
Oh, so
The
near
white and the
near one EV in this case, right? Or the orange line appears in the conduction band.
It's completely on zero at Lumo. The orange one does, at least to me.
This one?
yeah, that seems high enough, so you might not
So it's
see swapping of the.
even quantitatively it may not be affected. More questions?
I have a question. So what is the motivation of this research?
Just to evaluate the influence of electric field,
What?
to test the influence of electric field on the charge carrier.
Is it sufficient or you want
So the influence of electric field on charge carrier.
Yeah, you're free to these interfaces are parts of photovoltaic devices. Photovoltaic devices are assembled in sequential chains. Each of them generates voltage and current, and the individual unit cell works in presence of others. So typically, the regime of operation of photovoltaic cell is under external electric field. So an account of external electric field may change efficiency of photovoltaic cell.
Okay, so this is for this model, right?
Yes.
And this model is separate.
Combustion.
Combust.
What's the motivation for combustion?
So I guess at extreme conditions, the reaction mechanism is still not very clear. So we want to use ab initio molecular dynamics to get a deeper insight about the reaction mechanisms.
And this model is like this simulation cell is separate from the next one.
Which one?
So my question is not clear.
It is the same simulation cell at different time
No,
steps.
I know that this is the simulation cell. Is it separated from the next one or surrounding other cells? Is it isolated?
No. It's periodic boundary condition without vacuum between them.
So periodic boundary conditions like all 3D axes?
Yes. So if actual model will be
Continuous then?
continuous,
In all
like
directions?
eggs in a foam of the gas. So they will be separated by whatever 14 angstrom and more metal clusters. I can add if we burn methane for energy or for transportation, it needs to release maximum available energy into heat. But depending on the conditions of reaction, it may go into undesired direction. At the slide, at the first slide, the second panel, there is a formation of ethane. So methane, instead of burning, connecting with oxygen, it connects to itself with another methane and forms the experienced polymerization. it is interesting chemistry, but it is undesired outcome of the combustion process. In regular life, if you have a candle or kerosene lamp and put a glass on the top, it will develop this black soot of carbon.
Mhm.
So instead of burning, it just develops this carbon. It's not what you want. And if you study how this combustion goes on, one can control and intentionally create conditions of combustion that will prevent it from this polymerization. It will make clean 100% combustion, higher yield of. Is it good enough for motivation? More questions? If not, thank you once again. Okay, well, meeting is done. I'll stay here. I have a couple of urgent emails, but it will take 5 minutes, and then I will answer if there are any questions.